Now the 19th of June in North America, where most of the Organic Chemistry Explained followers are. So, hi, I hope your week's going well. If you're studying organic chemistry over the North American summer, then I hope it's going well. I'm just looking at the chat here. So photosensitivity says, do you do private tutoring? Yes, I do. So if you go to organicchemexplained.com/tutoring, then you'll see all the details of how I do tutoring. So I do it online. I use my tablet and a stylus to write out whatever we're talking about. So just let me know if you want any more information. You can private message me on Instagram if that is handy for you. So once again, it's organicchemexplained.com/tutoring. Or if you just go to the homepage, then there's a link to the tutoring there. So to those of you filing in, welcome. Thanks for coming along. So Workout Wednesdays. Every Wednesday at 8 p.m. Eastern Time in North America, I go live and answer whatever questions you have about organic chemistry. Feel free to send in your questions ahead of time, and I'll try to answer them on the stream. I don't go through a lot. I like to keep these short, so just 1 or 2 questions, and then I try to push out the recordings wherever I can. And I'm trying to push the limits of what you can do with I guess, live here, by going live to Instagram, Facebook, YouTube, Twitch, Periscope, everything I can at the same time. So hopefully if you're tuning in, wherever you are, then I hope things are going well. I hope you're doing well with your organic chemistry studies. And so let's get started. Okay, so I'm just going to move my little thing over here. And the first question I have to go through today is from the Facebook group Organic Chemistry Help. So I moderate an organic chemistry group called Organic Chemistry Help on Facebook. It's free to join. You can ask questions. There's over 1,500 members now, so it's really grown. I'm so happy to see everyone there talking about their problems with organic chemistry. And when I can, I jump in and I help out with those problems. So this question is from one of those users named Annie Bright. So hi Annie, thanks for the question. Really common question when you get to carbocations and carbocation rearrangements. So what we've got here is a 5-membered ring with a positive charge or a carbocation external to that ring, and then it has rearranged to a 6-membered ring. And this looks kind of crazy when you first see it. Like, how on earth does that happen? So what I want to do is not just show you how this happens, but I want to show you how you can deal with problems like this more generally. So what kind of strategies can you use for tackling mechanism problems like this? And the first hint I want to give you, the first key to doing these sorts of problems, the first strategy is to number the compounds. So number the starting material and number the product, because that will help you see where the various carbon atoms have come from and ended up in the product. Okay, so I'm going to do that. Now, where do you start numbering? Well, in a way, it doesn't matter too much where you start numbering. Just start numbering somewhere in the starting material and then look for common features in the product. And this becomes easier to do the more practice you do. So let's start numbering at the end here, close to the positive charge. 1, 2, 3, 4, 5, 6, 7. We've got back to that 1, 3, and then so we'll just number this one 8. Okay, now how do I translate that into the product? Well, it's not perhaps that easy to see, but I would expect that the 1 and the 8 would be places where things don't change. So they're both methyl groups. So they're at the end of a chain, and I've got methyl groups at the end of the chain here on the product. So I can number 1 and 8 to those positions around the product. Okay, so once you've done that, then let's just try numbering consecutively and see how that goes. So we go 1 to 2, 3, 4, 5, 6, 7. Okay, so it looks like we've got a bit of a movement of carbon 7 was attached to carbon 3 in the starting material. So let's just highlight that. So carbon 7 was attached to carbon 3 in the starting material, but now carbon 7 is attached to carbon 2 in the product. And we know that carbocations can rearrange. And so it makes sense that there must have been a rearrangement where that carbon 7 has moved from being bonded to carbon 3 to being bonded to carbon 2. Okay, so if I draw that with a curved arrow, I can show this carbon 7 with its pair of electrons moving over here to carbon 2, and that will get us this new bond. Now, that might be a little bit misleading, because what I would then think is, well, I should have a positive charge left on carbon 3, but it looks like my positive charge is on carbon 7. But because of the symmetry of this molecule, that is the same as drawing the molecule where the methyl groups are here like this and the positive charge is there like that. And so my numbering, works out either way. So if you get what I'm saying there. So please, if there's anything you're not sure about, just pop a message into the chat and I'll try to rework or re-go over things again. Okay, so what I want to do is draw out that migration going there, so that we've now got a bond between the carbon 7 and carbon 2. And the positive charge is left behind on a tertiary carbon with a methyl group attached to it. Okay, so what we started with was a secondary carbocation. And we know about carbocations that methyl is absolutely terrible and never forms, basically. Primary is almost as bad. It's really unstable. Secondary is a little bit better, but tertiary is where we really get some stability. And so when this rearranges from the 5 to the 6-membered ring, we go from a secondary carbocation to a tertiary carbocation. And that increases the stability, and that's why this rearrangement takes place. Okay, so just looking in the chat here, so we've got, sorry about being probably poor at pronouncing your names, but we've got Jayesh from India doing an MSc in chemistry, doing organic chemistry. Hi, Jayesh from India. We've got a student from Uruguay. Lovely to see people tuning in from South America. Thanks for joining in. We've got Lucas asking whether I speak Portuguese. So no, I don't speak Portuguese, but my wife is Brazilian and she speaks Portuguese. So I like to be inclusive, and so I tend to hashtag things with some Portuguese. And if you do ask anything in Portuguese, then I can try to get it translated by my lovely wife, Sylvia. So we got Berm_posters tuning in from America, Eastern Seaboard. Hi, nice to see you. Lots of people following the Organic Chemistry Explained Instagram and other accounts from North America, particularly from the Eastern Seaboard, all through the Midwest, right out to the Pacific. And I've got plenty of people following from Canada and other parts of the Northern Hemisphere as well. So hi, if you just joined in, we've just gone through a problem from Annie Bright from the Facebook group Organic Chemistry Help about carbocation rearrangements. I think it probably covers it. I'll leave it there. This question only asked for how we get from one carbocation to the other, so I won't go through what would happen from there, but you could imagine loss of a proton to then form a double bond, and so you could get to an alkene product via an elimination. So we've got Logan Dewberry-Reeves tuning in from Central Florida. So hi, I'm sure it's a lot warmer there than I'm in Brisbane at the moment. It's pretty mild climate here, but we're in the middle of winter and I'm feeling a bit cold. So I'd quite like to be in Florida at the moment, actually, although maybe it's a bit too hot at the moment. Let me know, what temperature and what kind of humidity are you going through there at the moment? Okay, so I had one other question I wanted to go through on this Workout Wednesday today. So I'll just scroll down to the second question. And this one comes from Kamal. So Kamal is a regular contributor to the Organic Chemistry Help Facebook group, and he sent this question in via direct message on Instagram. So get your questions to me any way you like. If you do happen to post them on Instagram as a post or as a story and link to my account, for doing that as a prize, I'll give you a copy of my structure drawing templates that'll help you draw really nice looking benzene rings, and they even have some chair cyclohexane templates to help you draw those chair structures, which is what we're going to do in a moment. Okay, so too hot. Yes, I can imagine. So I've never been to Florida, but I've looked at the average temperatures, and I think Brisbane is quite hot in summer, but actually a lot of Florida is even hotter and more humid. So I'm sure that it can get quite uncomfortable in the summertime. So hopefully it abates soon and you have some nice weather on the way. Okay, so we've got this question from Kamal. It's about two different cyclic alkyl bromides. So these are diastereomers. So they're different three-dimensional arrangements of the atoms where we can't interconvert them via rotating around single bonds. So they're not conformational isomers. They're also not mirror images. So they're not enantiomers. So the only thing that is left is that they must be diastereomers. Okay, and we're asked in this question, which one would undergo elimination faster with potassium hydroxide? So potassium hydroxide, we're talking about a fairly small base that's, probably in the moderate, medium range. It's not super basic, but it's not like a terrible base either. So it's going to prefer to go via an E2 elimination mechanism, particularly because we've got secondary alkyl halides, so they're not going to form a secondary carbocation very easily, but we've got a reasonably good base, so we can think about an E2 mechanism. Now, what do we need for an E2 mechanism? We need to have an I'll draw this out in parts, anti-periplanar arrangement of the proton that has been removed by the base and the leaving group, this bromide leaving group. So what we're going to have to do is draw out these molecules in the appropriate conformations and see, can we get that anti-periplanar arrangement easily? Okay, so I'm just looking at the chat here. So L Perez 4510 says, answer because it has stereochemical requirement. Exactly. We're looking for the stereochemistry of these compounds to see whether we can get an anti-periplanar arrangement. So thank you, Adam Z. Mom, who says anti-periplanar. You're right on the money with that one. Okay, so we want to look at the conformation. So let's look at A first. So just a bit of a recap. I've actually got a video on my website. If you search for how to draw chair cyclohexanes, I've got a really short video about how to draw chair cyclohexanes, and I've also got templates to help you do that as well. So what we want to do, if you're just new to this, what I really want you to focus on is what is the system for drawing a chair cyclohexane correctly. So we want to have parallel lines like this, okay, and I'm not the neatest chemist in terms of drawings, so it took me a long while to get these looking moderately correct, and I can certainly improve them as well. Then we want to draw a line going up towards that corner there, and a line going down towards that corner there, and then we want to make them meet up like this. Okay, and that's not perfect, but it's getting pretty close. And once you get better at this, like I'll actually draw chair cyclohexanes, not doing that sort of fairly slow way, but just sort of draw them like this, and they come out looking fairly good. But the important thing is that if you were to draw some grid lines here, then we would have horizontal line where those carbons are even. This is a bit wonky, but those carbons should be even like that, and we should have all the sort of pairs of lines parallel to each other so that it looks good. Okay, so I'll just get rid of those yellow lines there. Okay, so where do we go with this? Well, firstly, we have an up isopropyl group and an up bromide. So we want to draw those two groups both up. Do we draw them axial equatorial? So let's just pick one at random. So let's just draw an axial bromide. So we go straight up. Oh, I've still got the yellow color there. Let's go back to black. Up bromide, where it's axial. So how do we draw an axial substituents? The hints I want to give you are the axial bonds. If you draw out the chair the way I've shown you here, you have to draw the axial bonds vertically, either vertically straight up or vertically straight down. And they go away from the vertex. So if I have these bonds going like that, you can see they meet at a vertex, and we're going vertically away from that vertex to get the axial bond. And it's really important to do it like that, because if you start making it slant out like this, you're not showing a very accurate bond angle, And you're going to get marked down on an exam by your professor. So really try to ace these things from the beginning, and you'll do a lot better in the exam. Okay, so if the bromine is up axial and the isopropyl group is on the carbon next door and it's also up, then we need to draw that other one, the other substituent. I'll stick with red just to make it clear. We need to draw that other substituent equatorially. Okay, so if we go to the carbon next door and it's on the same face, we're going to alternate axial, equatorial as we go around the ring. So that isomer there is that's going to be one possible conformation of this molecule. Let's draw in the other one for completeness. So I'll just draw it here. We'll have a equilibrium where we have the bromine going down like this, and the actually I won't draw like that. That's going to be the other enantiomer. They'll get confusing. So when we do the ring flip, the axial bromide is going to go now equatorial. So we'll draw it like this, bromine going out like that, and then the isopropyl group is going to be up here like that. Okay, so now bromine is fairly big. Isopropyl group is fairly big as well. I would need to look up some energy tables, what are called A values, to know which one of these is more likely. But we can still say some things about how easy it is to get this elimination to happen just by looking at both of these possibilities, because what we need is the hydrogen to be anti-periplanar. So there's the hydrogen there. That would be anti-periplanar. Here, the axial bond is a carbon, and this one here, the hydrogen next door, is equatorial, so that's not anti-periplanar to the bromine. It's very much easier to see this with a model. So I really encourage you to get a model set if you're looking at questions like this to practice. On the adjacent carbon, we've got axial hydrogen and equatorial hydrogen. Neither of those are anti-periplanar to the carbon-bromine bond as well. So we have no hydrogens that are anti-periplanar to the bromine in this conformation. So that is not going to undergo elimination very easily. I'm just looking at the Instagram feed here, and sorry, the diagram has gone off the edge of the page there. So what I'm going to do is just redraw that for our Instagram viewers. So stick around for a moment. I'm going to redraw that. So we had a chair, cyclohexane. Let's try to get this all on the page. So we would have an up bromine, an up isopropyl, equatorial hydrogen, and axial hydrogen. And hopefully those you're watching on Instagram can now see that properly. Okay, so in that arrangement, okay, this one we don't get any easy E2 elimination because we don't have any anti-periplanar arrangements of the hydrogen and the bromine. However, this one gets a big tick that can undergo elimination very rapidly. Now, I'm going to delete this and give myself a bit more room and look at the B compound, the B diastereomer. So if we draw out our chair cyclohexane again, so draw it over here. Oops, that's looking a bit wonky. Do that again. Okay, now we have got an up bromine again and a down isopropyl group. Okay, that one is one conformation, and then the other conformation is where, oops, that looks wonky. Sorry, I'm trying to hurry this too much. Okay, there's a better chair. Now the other one is where we have a axial bromide and an axial isopropyl group. So it's important when we're drawing in our equatorial substituents, we want them to be parallel to the bond that's removed by one. So you can see this bond here is parallel to these two bonds here, and that's how we get the good angles for our equatorial substituents. Okay, so now what we've got is those two conformations. Now, between the two of those, Just checking our Instagram feed. I'm not sure whether it still is going or not, but between the two of those, we're going to have a preference for the conformation that has both of the large substituents equatorial. And in that conformation, we don't have any periplanar arrangement. So no anti-periplanar. And so that gets a big cross in terms of elimination. And in the other conformation, we do have an anti-periplanar arrangement of this hydrogen here, but we've got both of the substituents are axial. So we've got two axial substituents that are both large. And so that's a very unfavorable conformation. And so there's so little of that conformation that can undergo the elimination that it's going to be difficult for that elimination to occur via this E2 mechanism. So overall, the compound A should be the one that eliminates most rapidly. And it's going to eliminate two possible ways. We've got those two sets of protons, and probably the ones less hindered will be with a bulky base, the most likely to be removed. But with a small base like hydroxide, we're going to get Zaitsev's rule apply, and we're going to get an elimination to give the more substituted bond as the major product. So if I just scroll down a little bit, the major product of this reaction is going to be this one here. We have the isopropyl and the double bond there like that. So Zaitsev's rule will apply. Okay, so that's all I had to say about this. Just looking back at the comments on the stream. So thanks for joining in. Got a few thumbs up. Great to see you all here. So we've got, yes, stereochemical requirement. Yep. Oh, good. Okay, so that's all I wanted to do for today's Workout Wednesday. If you need any help with organic chemistry, go to my website, organicchemexplained.com. I've got useful tutorials there, some practice questions on topics. I do private tutoring, and there'll be more great things coming out for organic chemistry in the near future. Stay tuned next week for the Workout Wednesday, same time, 8 p.m. Eastern, and send through your questions ahead of time if you want to get them answered during the live stream. Okay, so have a good day and good luck with your studies. Bye-bye.